needed to try out this compensator. So we built it. Just, this is a good place to start at least. So let's try it out. Let's see how we do with this. So we could do another root locus. So one way to go here, we have a new compensator, could do a new root locus, could choose out our 20% overshoot again. It's really up to you at this point. If you want to do another root locus, that would be good. Another thing we could do is just try it and see what the simulation looks like. So I'm inclined to do that. So let's define a new K2, which we don't know what it is yet. We're just going to set it to 1. So we want to maybe tweak the gain again, but we don't know what to tweak it to. So maybe our percent overshoot is going to be met. Maybe it's not. Let's look at the simulation, see what happens. Let's see what our steady state error compensation is. That's the whole point of this integral control. The integral compensator is to see what happens in terms of the steady state error. So let's define a G closed loop. So here's our closed loop transfer function. This time it's going to be PI. So let's do PI, and then I'm going to call this one the PI. Well, no, we'll just do PI, and then I'll just change it because you guys are going to see the process here. Niles is wanting to play ball. Come here, come on. Oh, good boy. See, look. Are we recording? Yeah. I would love to play, but maybe after. One day, I'm gonna start bringing him to class. I think he's gonna do a really good job as like a professor assistant. Yeah, don't you think? Okay. So we were about to try this G closed loop PI. So our forward transfer function now. So we've got to use feedback. Our forward transfer function now is the K1 times K2 times CI. So that's our compensator. And now times the original G, our original plant. Okay, that's now our compensator and original gain controller, and the new K2, which is just set to 1 for now, but we're going to want to probably adjust. So, and then we have our original plant. Unity feedback still. Close that up, and now we're ready to do a simulation and plot of this. Now, we did YP. The YP is for the P controller step response. Let's do another one that's YPI for the proportional step response. And now we'll use the closed loop PI for that. And we'll plot them in the same figure and just compare what they look like. So let's look at the TA YP. We'll do hold on. Then we'll plot TAYPI. We'll make this blue, and we'll make this red, and we'll also do probably, we should just label some stuff, right? X label time, Y label step response, and we'll use a grid. Oh yeah, we should also probably do a legend, and the first one is going to be P control, and the second one is going to be PI control. So let's see how we did. Okay, so in 2 seconds, we're seeing a little bit of improvement in the steady state error. We are also seeing a very similar transient response to what we saw before, which is what we intended when we chose this very conservative integrator compensator. Now, we should verify that, well, so it looks like it's going to go to 0 steady state error, but it's not quite clear that it is. So that's 0 steady state error only a mother could love, I think. So let's see if we can simulate it a little longer and see maybe 4 seconds to see if we can convince ourselves that's going to 0. Yeah, so it's going to 0, but it's like slow, right? So like the transient happens and then it slowly oozes back to 0 steady state error, probably at time infinity, right? So we have, it's success, 0 steady state error, and transient response performance. So we started with, which is about 20% overshoot. So that's all good, but we might say, well, we'd really prefer to settle to our steady state value a lot quicker. Our settling time here is still not great, and that wasn't part of the original requirements, but say we suddenly realize, well, we actually care about that. So let's see how we would augment our PI controller to make that happen. So if we went back and we said, okay, so we'll go back to 2 seconds before I forget. 2 seconds, and let's look at let's move our 0 a little bit. So we have some space to work with, so I don't know. Let's move it by a factor of 2, say. Go to negative 0.7. That boy. Okay. And let's just see how we do. Okay, so faster. Let's move it a little more. Let's go to like maybe negative 1.5. All right, now we're getting somewhere. Settling to this 0-ish steady state error much faster, but we kind of sacrificed some, I think maybe some settling time here, and definitely our percent overshoot is above 20% now. It's like 24% or something. Not great. 23%. So we probably want to improve this. There are different ways we could go about it. So let's say we can essentially change 2 things. We can change our gain. So right now I have K2 at 1. So what we could tweak that a little bit. And if we increase that gain, we would hope to see our transient improve, but we don't know for sure if that's going to happen. We could look at the root locus and be a little bit more confident, but when you get to this point where you have this really rapid loop that you can close in terms of design, like you can tweak something and then check it, I kind of like to play with it a little bit if possible, and if it gets difficult, then you can go back and look at the root locus and see maybe if you can figure out what's going on. So let's increase it just by like 20%, our gain, and see how that affects it. So I think that it did improve maybe our settling time a little bit. Our rise time is actually better than the original P controller. However, as we increase the gain, it looks like we're going to increase our percent overshoot. So we might have to actually move our gain down a bit to like say 0.9. See how that works. Okay, so we got closer. So our transient response is similar to our original. I'd say without doing step info, just sort of looking here. Yeah, a little over 21% overshoot. So maybe we could bump it down to like 0.88. Like I don't know, maybe 0.85. It's really hard to say at this point. I think we just nailed it. Let's see if we check this cursor. Yeah, like we're right at 20% overshoot. 0 steady state error. Our transient is looking quite good. Our rise time is similar to that from our P control. So depending on what your requirements are, this is, maybe a better controller than, maybe this is a better value of gain than the one that we started with that has a slow steady state error compensation. This steady state error compensation is faster, but we had to adjust things a bit. So that's kind of the idea of doing a PI control. Just really depends on what your requirements are. And this method gives you a good sort of scaffold to work in terms of adjusting gains and coming up with a controller. So say that this is our final controller design. We could look at what it looks like. So GCLPI. So this is our closed loop transfer function. If we want to look at the compensator, our compensator is K1 times K2 times CI, right? That's the compensator that we developed. And it looks like this. There's a gain term, there's a 0 at negative 1.5, and there's a pole at the origin. So that is our PI controller. All right, so that's it. If you have any questions, send me a message. We're going to do this again when we do PID control, because it turns out when you do PID control, you also do PI control. I know. Okay, that's all I've got for this. See you guys Monday.